Ladies and gentlemen, welcome. In this lecture, is the seventh lecture, we'll be talking about continuity of functions. Well, we will have, I think, two more lectures after this. I'd like to, after this lecture, I'd like to talk about exponentials and logarithms. And then afterwards, I'll do a video lecture with only solving problems involving all the elements from this chapter. All right, so let's get started. So, well, this lecture will be a little bit longer, but I'm sure you will like it, hopefully. All right, so we're going to talk about continuity. And, well, we will see different type of properties here. I will dwell on quantitative properties, on qualitative properties. We will see also, we will be talking about the intermediate value property as well. You will see that continuity plays an important role to that. All right, so let's talk about first. The first thing we want to talk about is continuity of a function. Of a function at a point. All right. So we would like to talk about this, and we'll see. Well, geometrically, it's quite clear what for a function, what it means for a function to be continuous. In other words, its graph has to be. You cannot interrupt the graph, so it just keeps going. It never stops. So we say that a function f is continuous at a point, let's say x equals x naught, right? If the following three conditions are met. Well, I could just say all three of them at once, but let's put it this way. All three conditions are satisfied. All right. The first one is that f of the function evaluated at that point, so at this point at x naught, is defined. The second condition is that the limit as x approaches x naught of f of x exists. So this limit exists. And the third condition, which is more important, I would say, not just that limit exists, but moreover, it's the value of f at that point, at x naught in our case. So we can write this as the limit as x approaches x naught of f of x equals f of x naught. So that's the, I would say, the most important condition. So I could have just said it all three of them at once, but anyway, you can, all right. So this is the definition of the continuity at a point. Well, we can say that a function that is not continuous. So we would like to see what it means for a function, what it means for a function not to be continuous. So we say that a function is not continuous at the point x equals x naught is said to be have, okay, let me write it this way, is said to have a discontinuity at that point. Okay, so that's what it means. So in other words, if the function is not continuous at that point, then we can say that this has a discontinuity at the point x naught. All right, now let's see some examples. I would like to see some examples. And let me draw some pictures first. I want to recognize this property of continuity by just looking at some pictures. So let me draw the following picture. So let's just say that here we have this value f of x naught. Here's the point x naught. So they will meet somewhere here. Okay. And let's just say that I have the graph of this function. Okay, let me say that here has a hole at L. And let's just say that this function goes like this. All right. So that's the graph of a function. Just look at it. Well, let's see if the function, based on what we see in this graph, let's see if this function is continuous at the point x naught. Right? So we would like to see that. Okay, so now let's look at the graph. So the first one is f of x not defined. Well, it looks like it is. So we can say the first one, let me write it here, f of x naught is defined. But pay attention that we need to check all three conditions here. The limit has to be defined. All right, let's see. The second one, since the limit, and I'm going to look from, I'm going to take the left hand limit and the right hand limit. So since the limit, let me write it, since lim as x approaches x naught from the left, right, x not minus here, of f of x is the same as the lim as x approaches x naught plus of f of x, right? And moreover, this implies that the lim as x approaches x naught of f of x is L, some number L. So this limit exists. So this limit exists. And now the third one, we want to see if actually the limit of this, well, we want to see if L is in fact the value of f of x naught. Well, it looks like it has a hole there. So this implies that the limit as x approaches x naught of f of x is not the value of f at x naught. So f is not continuous at the point x equals x naught. All right. So you see it has a hole here. So let me mention this as a hole. That's why we have problems. Now let me draw another picture. There's something similar. So these are the axes. All right. So we have the following. Let's just say that the graph will look like this. And again, this has a hole here. It keeps going. So let's say this is x naught, right? Here is L. Well, in this case, as you can see, f of x naught is not even defined clearly. So we can say without any doubt that f is not continuous at the point x equals x naught. right? So this is another picture where the value at x naught does not even exist. Now let's draw some other two pictures. We want to see what kind of discontinuities we have. All right, let's think of the following scenario. Let's just say we have something like this. So let me think. Okay, so we have something like this. So we have the point, we have here x naught. And here we have f of x naught. So they meet somewhere. Okay, here we have this. So the graph would look something like this. And now here we have the value of the limit. Here we have a hole, let's say. And here the function will look like this, let's say. All right, so this is a graph of the function. Well, based on what you see here, the first thing first, f of x naught is defined, that's clear. Right? We have no problems about this. We don't have any holes, you see here. The second one, if we look at the picture, the limit as x approaches x naught of f of x, well, if you look at this, we have a hole, so we have a jump here. So the limit does not even exist, does not exist, right? Well, because, let's explain this. This happens because the limb, let's say the limb from the left-hand limit is not the same as the right-hand limit, right? So the second condition is not met. So f is discontinuous, let's say. So it's not continuous at the point x equals x naught. All right, that's great. And now, so we have a jump here. This is what happens. Now let's see when the fourth scenario. So let me draw the following picture. And here we have a pole, let's say. Let's say that here we have this. So this is the point x naught. And here and now the graph will look like this, something like this. And let's just say I have, again, some will look like this, let's say. All right, let's look at this picture. Well, you see we have here this guy here. This is a vertical asymptote. So let's write this. Note that there is a vertical asymptote at x equals x naught, right? So this implies that the limit, let's just say the left-hand limit, so the limit as x approaches x naught from the left of f of x is clearly infinity, and because you see the graph, it keeps going, and the limit, the right-hand limit, so the limit as x approaches x naught from the right of f of x will be again infinity. So, and even in this scenario, this means that that these two limits do not even exist. So the two one-sided limits do not exist. Okay, so therefore, my function f is not continuous at x equals x naught. All right, let's summarize everything now. Now, discontinuity occurs, let's point this as a remark. And this scenario, we'll call this is a pole. Here we have a pole. So in other words, discontinuity, to summarize everything, discontinuity occurs when there is a pole, hole, and jump at the point x equals x naught. All right. So these are the circumstances where, so as you can see in the first two examples, we have two holes, and then we have a pole and a jump and a pole, right? All right. So now you see what it means for a function to be continuous, what it means for a function not to be continuous. And we've seen graphically some examples, but now let's see some other examples, some concrete examples of functions which are, we would like to see if these functions are continuous or not. So we like to test continuity at a point. So let's, we said that test continuity, let's formulate it in this way. At the point, let's say x equals 1 for the following functions. All right. The first example, let's say f of x is, let's say, x squared plus 2x minus 3, let's say everything over x minus 1. Let's take this first function and let's look at it. Well, if we look at it, we need to see how this function is defined, right? You see, this is a rational function, and clearly we have a problem at 1, right? So clearly f is not defined at the point x equals 1. Well, because if we want to define this, well, we cannot plug in, but we can take the limit as x approaches 1 of f of x, and this will be nothing other than just 0 over 0, which is undefined. Well, but so this function is not continuous at x equals 1, so f is not continuous at x equals 1. Okay. Now let's see, well, this was easy. Let's see another function. Let's just say, second example. let's just take, for example, now g of x to be, well, the same function, x squared plus 2x minus 3. But now I'm going to tweak it a bit. So this will be the same function as previously, right? And this will be like a piecewise function. This f is equal to this rational function if x is not different than 1. And now this will be 6 f x is 1. So this is what we call a piecewise function, right? And we would like to see if this function is continuous at 1. So this is the question we would like to answer: is g continuous at x equals 1? That is the question we want to answer. So let's think a bit, because we have seen, I've said something about the limit of the function at x equals 1. Well, vaguely I said in the previous example, we said that this is indeterminate. But in fact, we can actually maybe compute this limit. So what we need to do, clearly g of 1 is defined, right? So we would like to answer this question, but first, clearly g of 1 is defined. Okay. But now, let's see further what happens, because we would like to see if this function is continuous or not. So furthermore, we have that the limit as x approaches 1 of g of x will be nothing else than just the limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. But now again, like we previously said, this will be an indeterminate, 0 over 0, so we can do something about it. Maybe we can factor the quantity, basically the numerator. This will be the limit as x approaches 1 of, this will be x minus 1 times x plus 3, everything over x minus 1. And this will be nothing else than just the limit as x approaches 1 of x plus 3. And this will give us 4. Now, we're not done. Keep in mind that we have the third condition, and that was the most important condition. So the third condition, which was the most important, was the following. The limit of the function at that point has to be equal with the value of the function at that point. In other words, what is g of 1? But g of 1 is 6, so 6 is not equal to 4. So it implies that the limit as x approaches 1 of g of x is not equal to g of 1 with the value of the function at that point. So g is discontinuous at the point x at x equals 1, and that's it. So you see another example of a piecewise function which is not continuous at a point, right? Now let's see some other examples. See, that was the second one. The third one. And here in the third one, well, I'll take this as you can imagine, so I'll try to make them to agree. So h of x, I'll take the same function. This would be x squared plus 2x minus 3 over x minus 1 if x is different than 1, and 4 if x is equals to 1. So again, a piecewise function is basically the same function as the previous one, but instead of 6, it's 4, as you can see, right? They're basically the same. So the question is h continuous at x equals 1? That is the question. Well, the answer, as you can imagine, based on previous considerations, it's yes. And well, that's the short answer, but why? Well, the limit, as let me put it shortly, as x equals 1 of h of x, which is the lim as x approaches 1 of this guy here, x squared plus 2x minus 3, everything over x minus 1. This guy, we computed previously, right? Look here. It was 4, but also this 4 is also h of 1, sorry. So this implies that h is continuous at x equals 1. So finally, we have continuity. All right. Now let's see another example of a function. See 4, example number 4. Let's just take the following. Let's just take f of x to be x plus 3 over, so again, a piecewise over x minus 1 if x is different than 1, and 4 if x is 1. The same question. Is f continuous at x equals 1? That is the question we want to answer. And we should be very, very careful here. Because so we will have to evaluate, well, that's clear that, so f of 1 exists. So clearly, f of 1 exists, and moreover, is equal to 4, as you can see in the function, right? Because it's defined in this way. But now the question that we would like to answer is if the limit as x approaches 1 of f of x is indeed the value of f at 1, which is 4. So next we need to compute the following limit. Lim as x approaches 1, whatever that means, from the left, from the right, anyway. We don't have any information about that. Of this guy is what? Well, if you plug it in, we have 4 over 0, which will be infinity, right? Well, depending if it's coming from the left or from the right. So it will be plus minus infinity, it depends. But in any case, the left-hand limit and the right-hand limit do not coincide. So in other words, it implies that the limit as x approaches 1 of f of x does not exist. Okay. All right, now let's see another example. Well, there in the notes, there are a bunch of examples. Maybe I will not dwell on all of them. Some of them are extremely trivial, and I'm sure you can read them in the notes and everything. But for example, let me just consider something easy, a polynomial function. Let's just say g of x is, okay, let me take the one from the note. So it's 7x cubed plus 3x squared minus 2. Well, is the function continuous at 1? Well, it's quite clear that the lim as x approaches 1 of g of x is the same as the lim 7x cubed plus 3x squared minus 2, which is, well, if you operate with all these, we apply the properties of limits of functions, this will be nothing other than just 7 times the lim as x approaches 1 of x, everything cubed, plus 3 times the lim as x approaches 1 of x, everything squared, minus 2. So this would be nothing else than just 7 plus 3 minus 2, which will give us 8, right? So this is 8. So in other words, if you can also compute the value of this, so let's do it. Also, the g of 1 is 8 as well. So g, the function g is continuous at the point x equals 1. Anyway, that was easy, very easy. All polynomial functions, any polynomial function that you pick will behave like this. All right, now let's, well, we have seen a bunch of examples, and now I would like to veer towards some theory. So I would like to talk about some theorem regarding continuous functions. And the first theorem that I have in mind is the following. So theorem, if f, speaking earlier of polynomials, and if f is a polynomial, a rational function, let's say a power function, a trigonometric function, or an inverse trigonometric function, then guess what? In other words, all these functions that I just mentioned here is what we call elementary functions. In other words, if f is an elementary function, then guess what? Then f is continuous. Then f is continuous. But any number say x equals x naught, for which f of x naught is defined, right? In other words, all elementary functions what did I write here? Elementary are continuous. All right, so we have this. So keep this in mind. This is what you have to know, that all elementary functions are continuous. So that's basically what we just stated. And now we would like to see what kind of properties, for example, what kind of properties do we have for continuous functions when we operate with them, such as if I have the sum of two continuous functions, is the sum still a continuous function? Or if I have the product, or if I multiply by a scalar, or if I take the quotient or the composition and so on. Well, this will be, okay, let me put this theorem 1, theorem 2. So properties of continuous functions. Well, if f and g, let's consider two continuous functions. If f and g are functions, are continuous functions, x naught, right? Then the following functions are also continuous. At x equals x naught. And we would like to see what kind of functions. We'll say, well, the first one, let's say, is a scalar multiple. Which is basically for any constant, let's say, lambda. So these are the scalar multiple, right? Then we like the sum and difference. Is also continuous function. So basically we have f plus minus g. And then we have the product, which is nothing other than a f times g. Then we have the quotient, f over g. Well, provided that that g of x is not 0. And we also have the composition, which is f circ g, or if you want, f composed with g of x, right? Well, provided that, here we provided that g, oops, provided that g is continuous at the point x naught, and f is continuous at the point g of x naught. All right. So these are the basically, well, they're quite expected. This is quite expected. Also, I'd like to talk a bit about the composition of, about the limits of a composition of two functions. So let me say the composite limit rule. Okay, which says the following: if the limit as x approaches x naught of g of x is L, and f is a continuous function at L, then guess what? As you can imagine, the lim as x approaches x naught of f of g of x is f of L. Well, that is, let me write it in this way: the limit as x approaches x naught of f of g of x is f of L, or if you want, is f of, and I'm going to write here the limit as x approaches x naught of g of x. So that's what we have. Okay. Right. So these are basically the basic properties of continuity, right? So the basic operations with continuous function. And now I would like to talk about one-sided continuity before we do more examples. One-sided continuity. All right. So this the function f is continuous from the right, let's say, from the right at the point, let's say, x at x naught, if and only if, so pay attention here. So it's both ways, if and only if the limit as x approaches x naught from the right, so it's x naught plus of f of x, is nothing other than f of x naught. So we have this notion of continuity from the right, and as you can imagine, we also have continuity from the left, so it will be similar. And it is continuous. From the left. At x naught, right? If and only if, well, guess what? The lim as x approaches x naught from the left of f of x will be again f. Maybe I should have said. All right, so that I wouldn't make any confusion here. Let me put x1 from the left is f of x1. All right, let me draw a picture so that things will be even clearer. So these are the definition, the formal definition. Now let me draw a picture for what do I mean by continuity from the right and continuity from the left. So let me draw the following pictures. I like to draw two of them, but anyway. So let's just say we have this point here, x naught. And here we have f of x naught. And the graph will be something like this, right? Let's say it goes like this, right? So that's what it means, continuity from the right. So this is continuity from the right. At x equals x naught. And now, well, let me draw a similar picture. Hopefully I have enough room here. Well, maybe I don't that, but anyway. So let me just consider this point here, x1. This is f of x1. And let's just say I have the function like this, right? Right, this is what it means, continuity from the left. So this is continuity from the left at x equals x naught, right? All right, so these are the two pictures. Well, I think it's quite clear when you look at them, right? And now I would like to even to talk a bit more about continuity. So let's see what it means for a function to be continuous on an interval. So we will talk about continuity on an interval. Okay. All right. Let's see. First thing, continuity on an open interval AB, let's say. Well, we say that the function f is said to be continuous on an open interval. Let's just say this open interval AB. Okay, if it is continuous, well, as you can expect, on each number on each number okay, at each number, at each number in this interval. Well, that's obvious. Well, the same happens if we have, so the same is true for continuity on let's just say half open interval. Let's just say it's closed at A and open at B, right? So we will include A, but excluding B, right? The same thing happens. And also the same thing, or the same thing will happen on closed interval. AB. So this time we'll include those two values, the endpoints A and B. So this will be nothing else than just the open interval reunited with these two endpoints A and B. Right, so we include both. So if f is continuous, we'll say that a function f is continuous on a closed interval AB if it is continuous at each number in this interval, including both A and B. Right? Okay, I'm not gonna write it. I think you can. It's quite clear what I mean by that. And now let's see some examples. And again, I'll draw some pictures so that you can see it better. The first case. Let's just say I have something like this. So let's say here I have A, here I have B, and they will meet the graph of the function. Let's say here I have a hole. Let's just say here, okay, let me put it this way so that, and here I have a hole as well. Anyway, so the graph of the function will go like this through these 2 points. Let's just say it's like this. This is the graph of f, right? As you can see it in the picture. So as you can see, I have a hole at both the endpoints A and B. So this means for my function to be, the graph is not interrupted. So this is continuous on an open interval AB, right? Okay, now let's see the second example. I think I have to draw it here. Let's just say again. Let's just say I have here, let's say this is A, and this is B. And let's just say I have here a hole, so this will go like this, the graph of f. This is the graph of f. So this is what it means to be continuous. As you can see, I have a hole at B, so it's not continuous at the point B, so it will be continuous. Continuous. On the interval closed at A, open at B. And now let's see some, so we have two scenarios left. Let's just say we have here A, here B. And let's just say we have something, the function will go like this, right? So this is the graph of my function, and it keeps going. So this is what it means to be continuous on the closed interval AB. As you can see, I don't have any holes in this. And now let's see what it means for the last scenario. Oh man, I drew some pictures here. Let's just say we have something like this. Here I have A, here I have B. So let's just go draw these two vertical asymptotes, and the function will look like the ouch, never touches it. So this is what it means for a function to be continuous on open interval AB, right? All right, so these are the four scenario, right? We see on the of continuity on the interval. Well, and we can see some examples. Let me draw some pictures. So examples. Find the intervals on which each function, each of the given functions is continuous. So we'd like to see which one of the following functions is continuous. And now I'm just going to draw some graphs here. And let me just say the following. So, okay, let me draw the following graph. Let me just say, so here I have the point -1, here I have 1, and the function here I have a line will look like this. Here I have the point, let's say 3. The function will look like this. Anyway, it goes here at 1. And from here, it's a line. So what do you think? Let's look at the graph of this function. Do you think this is continuous? Well, the graph looks quite is not interrupted, right? So it's a line, then at -1, so it's connected somehow. So definitely this is continuous. So in this case, we say that the function is continuous. Let's write it in this way. So the function is continuous on, do you see any discontinuity here? No, not quite. So it's continuous on R, on -infinity, infinity. We have no problems. Now let's see another one. Let me draw the following graph. All right, so we'll have the following. So let me just say here I have 1/2, here I have 1, here I have 3. And let's just say that here at this point, I have a hole. So, and here the graph will look like this. At 3 will look like this. Okay, and from here it will look like this. Okay, so you see. So what do you think of this? When you look at this, you see we have a hole here. Look at it. So we have problems at 1. So in other words, the function will not be continuous at 1. So the function is continuous everywhere but 1. So it's continuous on -infinity 1, open interval, united with 1, positive infinity. So you see we're excluding everything but 1 because we have a problem with 1. Now let me draw another picture. Well, so let's say we have the following scenario. So let's say we have the point 1 here, and here we have a point. And here we go with this, and here I have a hole. The function goes like this. And from here we have function goes like this. So let's look at this graph. What do you think? Well, as you can see again, I have it will be continuous, but it will be continuous on, so this means the function is continuous. On the union of, so on negative infinity 1, closed interval at the 1, as you can see, we don't have a hole here. But when we try to go on the other side, we have a hole. This will be union with 1 and infinity. So this is where the function is continuous, right? Now let's see a concrete example of another example of when a piecewise function is continuous. So we'd like to see that, or at least we'd like to see when the function is discontinuous. So let's do it. Let me think of an example. Okay, let me, yeah, I will take an example from the notes. So let me consider the following function, let g of x to be equal to, and we're going to take the following piecewise function, 2 minus x if, okay, so if negative 5 is less than 2, less or equal than x, and strictly less than 2, and x minus 2 if 2 is less or equal than x and less or equal than 5. So just look at it. What we're interested in, we're interested in the following two things. The first one is to discuss the continuity at the point x equals 2. And the second one is to find the intervals on which g is continuous. All right. So these are the tasks. We need to perform these two tasks for this problem. Let's look at it a bit. Okay. Let's see the first one. So let's see how this function is defined. All right. Let's see. Clearly, g of 2 is what? Well, it will be 2 minus 2, which will be 0, right? As you can see, it's on the second piece of my function. So g of 2 is defined. And it's actually 0. Now we would like to compute the limit. As you can see, this function is defined with these two pieces. So we would like to compute the limit at 2, but you see, we would like to see what's going on the left of 2 and on the right of 2. So we have to compute the left hand limit and the right hand limit. So we have the following. The limit as x approaches 2 plus, let's say, of g of x. And let's see, so this would be the lim as x approaches 2 from the right of x minus 2. And this will be 0, as you can obviously see. And let's see what happens with the left hand limit. So the limit as x approaches 2 from the left of g of x, and this will be nothing else than just the limit as x approaches 2 from the left of, and let's see, these are the values less than 2 of 2 minus x. And if we plug it in, we get the 0. So this implies that the limit, since both of the left hand, the sided limit agree, this implies that the limit as x approaches 2 of g of x exists, and it is equal to 0. But also, keep in mind that g of 2 is 0. So we're combining these two. It implies that the limit as x approaches 0 of g of x is g of 2, which is 0. So this implies that g is continuous at x equals 2. Right? So the second part will follow immediately. G is continuous on the interval -5 closed and 5 open, because it's not defined there, so we don't know what's going on. Anyway, that's it. Well, if we like, we can draw a picture for this, and let's do it. So graphically, this means that, let's draw a picture. It's going to be a big one. Let's draw a big one so that you can see it clearly. So we say have here the point, 2, and we said that this is continuous at 2. We have this vertical asymptote at 5. This is the point 5. And also we have here at -5. Here's the point -5. Okay. And let's see how this function behaves. So here we have the point here, let's say -7. Right. Now here, let's say we have 3. So the function will go like this. Let me just draw it. Ouch. It will meet, oh my God, meet the point. Well, this should be a line anyway. And here we'll go here and here. So as you can see, this is a continuous function on the interval -5, closed interval, closed at -5 and open at 5. Anyway, this is there is another example in my notes. There are 2 of them. Both of them are very, very similar. So I would like you to check the other example. So there are 2 examples. I did the second one, and the first one you could look in my notes. It's basically the same thing. Now, since I don't want to lose too much time, I want to veer towards something else, and I'd like to talk about something more qualitative, which is called the intermediate value theorem. Well, in other words, well, let me just state it, and then I'll draw a picture. You'll see graphically what do I mean by the intermediate value theorem, because it has a really nice interpretation. So let's just write it first. If f is a continuous function, intermediate value, this is due to, I would like to say this, to this French mathematician called Gaston Darboux. He invented this notion of intermediate value property of a continuous function. Well, it's something, let's say, I will not exaggerate, but let's just say something very, very close to continuity. In fact, continuity implies that a function has an intermediate value property, and you will see exactly what do I mean by that. But anyway, let's just write it first. So if f is a continuous function on a closed interval, a, b, and L is some number strictly between f of a and f of b, right? Then there exists at least, let's say, one number c, which is in the open interval ab, such that f of c is L. In other words, we have the following. If f is a continuous function, on some closed interval, let's say AB, then f of x must take, in fact, let me emphasize this. All the values between f of a and f of b. This is important here. I want you to look at it. So this is what it means for a function to have the intermediate value property. This is what we say. And now I would like to draw a picture so that you can understand this better. And I think the picture will make things clear. And then we will see why is this important. All right, so let's draw the picture. So let me draw a big one again, because I want you to see I want this to make as much sense as possible. So let's just say we have here A, let's just say we have here B. Okay, so now let's just say here we have f of B. Let's just say we have here f of A. So here I have this, right? This point here of coordinates A, f of A. Let's just say we have here the other one here, B, f of B. Let's just say we have another, let's say we have an L here. In fact, wait. Let's say we have L here, and then we have C here, right? And then we just say that the function, let's draw the graph. Right? So suppose this is the graph of the function. I think it's quite clear. As you can see, for any value L between, so there exists a number C and A, B such that f of x takes all the values between f of A and f of L, right? You have f of C will be L. So that's exactly what it means. Okay. Now the question is, why do we care about this intermediate value property? And well, one reason is the following theorem, which will concern the root location theorem. And this will be very important. Basically, it says the following. Well, let me just explain it. Well, if we have a continuous function that comes from the negative and it wants to go to positive, it has to go through for 0. So in other words, if f is continuous on, let's say, a closed interval a, b, right? And if f evaluated at the endpoints, and so if f of a and f of b have opposite, this is important, opposite algebraic signs. In other words, their product is negative. One negative, or let me just say this. One is negative and the other is positive. Right? And then we have a root for f. Then f of c is 0 for at least one number c, right? In the open interval, so say open interval AB. So that's exactly what it means. And now let me just draw. This is a very beautiful theorem. Look at it. And we will see a bunch of examples how to apply this theorem. In fact, I'll show you one example. And I believe there are plenty of them in the book. In fact, when we will have the review session for before the midterm exam, probably that's going to happen in early November, I will show you more examples on how to use this theorem. All right, let me just draw a picture now, some pictures, and then we'll do an example. So let me draw the following. So let's just say here I have A and this is B, okay? Here is 0, and let me just say that, okay, let me go like this. So I have this here, this here, right? And you see it has to go through 0, so this is my point C. Or if you want, let me draw another picture. Okay, let me check. Oh my God. All right. So let's get back to our root location theorem. So now you see this first example. If you look at this first graph, you see it has only 1 0. But now let's draw one when we have 3 zeros. So let's just say we have here A. And let's just say the function will start from here and it will go like this, then like this, then let's cross one more time, and here we have B. Right? So here we have C1, C2, C3, right? So it has 3 roots here, but we said the theorem says that it had a function which has basically the intermediate value property, will have at least one root. Now let's see an example. How do we operate with this? For example, show that the function f of x, let's just its cosine of x minus x cubed plus x, has at least one root, or let's say one solution, so that it has at least one solution on the interval, let's say pi over 4, pi over 2. Well, when you see a statement like this, and trust me, you will get a statement similar at the midterm exam, not at the gateway exam. So the gateway exam, you only need to compute the derivatives of functions. But anyway, we'll get there once we finish with this chapter. Well, at the midterm exam, definitely will give you a problem like this. So I want you to pay attention. All right. So look at the function. The function clearly is continuous, right? Because we have operations with continuous functions. In fact, I'm going to leave this to you. Clearly, the function f is continuous. And I'll leave it to you to figure out why. We will figure it out why is this function continuous. Just like I said, cosine is continuous, x cubed is continuous, x is continuous. We have operations with continuous functions, which will give you a continuous function. We have said this based on everything we have just said. All right. So the f is a continuous function, and now I want to use the root location theorem. So what I need to consider is to evaluate. So next, we need to evaluate f, the function f, at its two endpoints. And if you look at the endpoints of these two this function are pi over 4 and pi over 2. And what we need to do, we need to take the product, or we need to show that f of pi over 4 and f of pi over 2 have opposite signs, right? Because keep in mind, look at the theorem again. We want to apply the root location theorem. So look here as it is underlined in red even. So have algebraic opposite signs. So one of them is negative and the other one is positive. So if this happens, then we will have a root between those two numbers. All right. So let's apply the root location theorem. So let's see. F of pi over 4 will be equal to what? Will be cosine of pi over 4 minus pi over 4 everything cubed plus pi over 4. Well, according to some computations, this would be approximately 1.008. And now if we compute f of pi over 2, this will be nothing else than just cosine of pi over 2 minus pi over 2 squared plus pi over 2, which is approximately negative 2.305. Well, this is what it says in the notes, okay? Well, as you can see, one of them is positive, the other one is negative, so they have both f of pi over 4 and f of pi over 2 have opposite signs. So by the root location theorem, it follows that there exists, or let's say, a number C in this open interval, pi over 4, pi over 2, right? Such that f of C is 0. And that's it. So f of x, oops, we want so we said that, sorry about that. So we said that, so this implies, so f of x has at least one solution in the interval pi over 4, pi over 2, right? All right, and that's it. Okay. All right, I think this sums up the lecture for today. Well, as you can see, I have some technical difficulties, but anyway. Well, this is the continuity. There will be 2 more lectures because at the end of each chapter, I would like to cover some of the, to do some problems, since we would like to see what kind of applications do we have. So the next lecture will be about these 2 functions, about the exponential and the logarithm. And then the last lecture will be about, we'll do only problems with the notions that we have learned in chapter 2. All right, I'm going to stop here. Thank you very much.